So we want to look at this flea in flight problem. So what we'll do is we'll start by sketching the idea. So we have a flea in flight. So we've got our little flea here. I'll just make it as realistic as I'll be able to do. And it is applying an initial velocity v naught while we have some acceleration due to gravity here. A equals, and we'll use the negative g convention for this. And it will rise to some maximum height. So for part A, the factors that we're solving for this v naught. So v naught is our variable of interest, and our h is 0.500 meters, and our a is negative 9.80 meters per second squared. So we look at our kinematic equations, and I think a good thing to realize is while this is in flight up here, it reaches this turning point here. The component of velocity in the y direction is 0. We could also say if Vf equals 0. And this lets us really center in on the Vf squared equals v naught squared plus 2a delta x. And delta x in this case is the height that it obtains. So plugging this in, we get 0 equals, well, let's actually, Vf goes away, that gets 0. So we'll use the nature saying, well, if that's 0, then v naught squared is going to equal negative 2a delta x. V naught is going to be the square root of this. And a negative, so we get 2. And negative times a negative is a positive, so 2 9.80 times 0.5, which equals second square root 3.13 meters per second. So that kinematic equation worked well. Now we can take this initial velocity and we can figure out the time of flight using the quadratic equation. Or we can look at this from another aspect, which is this flea is hopping up. It reaches the top and it free falls down. The fact that once it gets to the top, its motion is stopped. So from that point on, we can think it's dropping. So in part B, we can look at a flea starting at the top. So x naught equals 0.5 meters, x equals 0 meters, and v naught is 0 meters per second because it's at the top getting ready to start a free fall. And so if we use the x equals 1/2 at squared plus v naught t plus x naught, this portion goes away, and we can then solve for t. So 1/2 at squared equals x minus x naught, which is our delta x, or 0.5 again. So we're getting it back in terms of the original. So t squared equals delta x, 2 delta x over a. T equals the square root of 2 delta x over a. But a thing we want to note about all of this is the time for it to fall from the top to the bottom. The nice thing about our kinematic equations, in a constant acceleration, they're symmetric. And so this symmetry means that the time from the top to the bottom, or from the bottom to the top, is equal. Well, we want the total time. So our final answer, our big T total time, is going to be 2 times the little t we just solved for, which is the same as saying 2 times to square root of x over a. Square root of delta x over a. So, we've got this into a format that's nice for a calculator. I'll multiply by 2 times the square root of 0.5 times 2 divided by 9.8. I get 6.3887, or to the negative first, or 0.639 seconds. And that's our flea in flight.